Hello, welcome to this video. In this video, I'll be discussing on the Faraday's laws of electrolysis. But before I go ahead, I want to encourage you to do well to subscribe to this YouTube channel, as I'll be posting subsequent videos that can help to improve your performance in chemistry and in science. And also do well to like this video and recommend it to others that can also benefit from it. So just like I said, in this video, we're discussing on the Faraday's laws of electrolysis. I want to believe this is not your first time hearing this particular topic, but by the end of this video, you would have understood this concept more than you did before. So let's get started. Now, the first thing is to define the concept of electrolysis. What exactly do we mean by the word electrolysis? Now, electrolysis is simply the thermal decomposition of an aqueous substance by the passage of electricity. Now, take note of the following. Take note of thermal decomposition. Take note of aqueous substance. Then take note of the word passage of electricity. So now let's define electrolysis again. I said electrolysis is the thermal decomposition of aqueous substance by the what? Passage of electricity. Now you have to take note now that this passage of electricity end up leading to the migration of ions. It leads to the migration of ions, and this migration of ions ends up leading to the deposition of substances. So which simply means that when electricity is passed through an aqueous substance, now this aqueous substance now is usually referred to as an electrolyte. Now when electricity is passed through this electrolyte now, it then leads to the thermal decomposition of the electrolyte, which then causes the migration of ions and hence the deposition of substances within the electrolyte. So this explains the concept of electrolysis. Now, Faraday's first law of electrolysis. So the Faraday's first law of electrolysis states that the mass of substance deposited is directly proportional to the quantity of electricity that is passed through the electrolyte. So we can write this as M representing the mass of substance, which is directly proportional to Q representing the quantity of electricity that is passed through the electrolyte. Now, what does this law mean? It simply means that the more the quantity of electricity that is passed through an electrolyte, the more the mass of substance that will be deposited by the electrolyte. I hope we get that. Now, this quantity of electricity Q can be determined by the products of the current passed through the electrolyte, that's current I, and the time taken for the current to pass through, that is denoted by small t. So which means we have Q equal to IT. I'm very sure this is not your first time of seeing this particular formula. So which means we can rewrite the Faraday's first law of electrolysis as M directly proportional to IT. So if we go ahead to solve this mathematically, we'd have M equal to KIT, where K now is the what? The chemical equivalence. The chemical equivalence, which happens to be a constant. Don't take note of that now. There are important things that you also need to take note of in the Faraday's first law of electrolysis. Number one, it is important to take note of the units. This is very, very, very important. Now you have to understand that the mass is always in grams or kilogram in some other situations, and then the current is always in ampere, that is capital A. Then the time taken is always in seconds, that is small s. And then the quantity of electricity is always in coulombs, that is small c. So the repercussion of this is that you must ensure that while solving questions on Faraday's first law of electrolysis, you must ensure that all your parameters are in the right units, especially the mass and the time taken. So sometimes you'll be given a time taken in minutes or even in hours. So it is your responsibility to ensure that you convert those parameters to the unit that is needed in solving the questions. So for mass, it is grams. Then for time taking, it is seconds. Very, very important. Also, it's important to take note of the chemical equivalence, which is the constant K, which can be denoted by a formula. Now we have K equal to RAM divided by Faraday times valency. Now this valency can also be referred to as charge. Now let me give a further explanation of this. Now what do we refer to as Faraday? Faraday is simply the minimum quantity of electricity required to liberate 1 mole of a singly charged ions. I repeat, the minimum quantity of electricity as determined by Faraday, which is required to liberate 1 mole of a singly charged ion. And this minimum quantity of electricity is found to be 96,500 coulomb. 96,500 coulomb, which is the minimum quantity of electricity that is required to liberate 1 mole of a singly charged ion. Now, what do I mean by a singly charged ion? You have to understand that we have various types of ions. We have the uh, monovalent ions. Example of monovalent ions, we have Na plus, we have Ag plus, we have Cl minus. These are ions with the valency of 1. Also, we have divalent ions. These are ions with valency of 2. We have likes of Cu2 plus, we have Mg2 plus, and others. We also have trivalent ions. Examples are Al3 plus, right? So the effect of this is that depending on the valency of the ion, the number of Faraday required to liberate 1 mole of that ion changes. So for monovalent ion, take for example Ag plus, which will afterwards to take 1 electron to form 1 mole of silver. So which means the quantity of electricity required to deposit 1 mole of silver here is actually 1 Faraday, which is equal to 96,500 coulomb. But let's look at the divalent ion now. If we take for example copper ion Cu2 plus, which we afterwards gain 2 electrons to produce 1 mole of copper. So what this means is that copper ion will require 2 Faraday to liberate 1 mole of itself. So that 2 Faraday now will be 2 times 96,500 coulomb, and that will be equal to 193,000 coulomb. So this explains the effect of the valency or charge of the substance that is being deposited. So it's very, very important to take note of this. So that means now that, remember that we said that M equal to KIT, right? And we also said that K is equal to RAM, which we can also denote as capital M, over Faraday times valency V, right? So by the time we combine these two formulas, we have that the mass of substance deposited M is equal to capital M, which is the relative atomic mass, times I, which is the current, times T, which is the time taken, all over F, which is 1 Faraday, times V, which is the valency of the substance that is being deposited. So with this formula now, we are able to calculate the mass of substance deposited in an electrolyte when electricity is made to pass through it. So this explains the first law of Faraday for electrolysis. Now, without wasting time, let us move to the Faraday's second law. Now, what does the Faraday's second law state? Now, the Faraday's second law states that if the same quantity of electricity is passed through different electrolytes, the masses of substances deposited are directly proportional to their chemical equivalent. Which means when we have two different electrolytes, take for example, and then electricity is passed through those two different electrolytes. Now the mass of substance deposited by each of these electrolytes is directly proportional to the chemical equivalence E of the electrolyte. So which means that mathematically we have M equal to Ke, and we have K equal to m over e, right? So in the case of two electrolytes now being compared, then we have m1 over e1 equal to m2 over e2. Or this can also be written as m1 over m2 equal to e1 over e2. So we have m1 to be the mass of substance deposited in electrolyte A. We have E1 to be the chemical equivalence of electrolyte A. We have M2 to be the mass of substance deposited in electrolyte B, and we have E2 to be the chemical equivalence of electrolyte B. So with this formula, we are able to compare two different electrolytes based on the mass of substance deposited and their chemical equivalence. Now, to further buttress on this law, it's also important to take note that the chemical equivalence E can be equal to the atomic or molecular mass, which can be denoted by capital M, divided by the valency or charge, which can be denoted by small v. Now, what is the effect of this? Remember that earlier we mentioned that m, small m now, which is the mass of substance deposited, is directly proportional to the chemical equivalence, right? Which then mathematically means that m is equal to ke. But now we say that if we have our E to be equal to capital M over V, which is atomic molecular mass over the valency, then by the time we substitute this into this, then we are going to have that small m, which is the mass of substance deposited, is equal to K times capital M over V. So by the time we divide both sides by the capital M, by the time we divide both sides by capital M, then we are going to have that small m over capital M is equal to K times 1 over V. And small m over capital M is the number of moles, which is given by mass over molar mass or molecular mass, as the case may be. So which means that Faraday's laws of electrolysis can also be restated as the number of moles N being inversely proportional to the valency or charge V. So we have N equal to K over V, and we have K equal to N times V. So which means when we are comparing two different electrolytes now, we would have that N1 times V1 equal to N2 times V2, which can be written as N1 over N2 equal to V2 over V1, where N1 is the number of moles deposited in electrolyte A. We have N2 to be the number of moles deposited in B. We have V1 to be the valency or charge of A, and we have V2 to be the valency or charge of B. So this now can also be used to calculate the second law by Faraday for electrolysis. So having explained this now, we can now go ahead to solve some questions on the two laws of Faraday. Now let's solve this question that we have here. It states that a current of 2 ampere is passed through a copper sulfate solution for 25 minutes. And then we're asked to calculate the mass of copper deposited. So the first step is to write out the parameters given to us in the question. So in the question, we're given the current I to be equal to 2 ampere. We're given the electrolyte to be copper sulfate solution, that is CuSO4. Then we're given the time taken T to be 25 minutes. And then we're asked to calculate the mass of copper deposited. So with these parameters now, we can go ahead to solve this question. The first thing is to ensure that all our parameters are in the right units. So we need to convert the time from minutes to seconds. So we do this by multiplying the time by 60 to convert from minutes to seconds. And that will be equal to 1,500 seconds. So having converted our time to 1,500 seconds now, we can go ahead to calculate the quantity of electricity that is passed through the electrolyte. That is Q equal to IT. And that is equal to 2, which is the current, times 1,500, which is the time taken. That will be equal to 3,000 coulomb of electricity that was passed through the electrolyte. And then the electrolyte given in the question, we're able to identify the ion to be Cu2 plus, which is a divalent ion, which means it will gain 2 electrons to produce 1 mole of copper, which means that the quantity of electricity required to deposit 1 mole of copper is 2 Faraday, which is equal to 2 times 96,500 coulomb, and that's equal to 193,000 coulomb. So with this now, we can now draw out our relationship between the quantity of electricity required to deposit 1 mole and then the quantity of electricity that was actually passed through the electrolyte in the question. So we would have that 193,000 rather coulomb of electricity deposits 1 mole of copper, which means that 193,000 coulomb of electricity deposits 64 gram of copper. You understand that a mole of copper actually contains 64 gram because the molar mass of copper, or the atomic mass rather of copper, is 64. So now we would now say that 3,000 coulomb of electricity, which is the quantity of electricity that was passed through the electrolyte in the question, we will deposit X gram of copper, which is the mass of copper deposited that we were asked to calculate. So from here now, we can now solve for our X. So we have X to be equal to 3000 times 64 divided by 193,000. So if you solve this mathematically, you have your X to be equal to 0.994 gram of copper, which is approximately 1 gram of copper that will be deposited by 3000 coulomb of electricity that was passed through the electrolyte in the question. So this gives us our final answer. Now let's solve this next question. It states, how long will it take a current of 3 ampere to deposit 1.2 gram of copper? So we'll start by writing out our parameters for the question. So we have the question, we're given the current I to be equal to 3 ampere, and then we are given the mass of copper deposited to be equal to 1.2 gram, and then we are asked to calculate how long it will take. That means we are calculating our time t. So you can see this is slightly different from the first question that was solved, where we were required to calculate the mass deposited. In this case now, we are required to calculate how long the current was passed through the electrolyte, which means that we don't have a value for our Q. Remember that Q, which is equal to IT. So to calculate the quantity of electricity that was passed through, we need the current and the time. For in this particular question now, we were not given the time. So that means we don't have a value for our quantity of electricity that was passed through the electrolyte. And also, you remember from the first question that Cu2 plus, which is a divalent ion, requires 2 Faraday to deposit 1 mole, which is equal to 193,000 coulomb of electricity that is required to deposit 1 mole of copper. So we can now go ahead with our relationship by stating that 193,000 coulomb of electricity deposits 64 gram of copper. That is 1 mole of copper. Then we would now say that X coulomb of electricity will deposit. Now in the question we're given the mass of copper that was deposited, which is 1.2 gram of copper. So with this now, we are able to calculate the quantity of electricity that was passed through the electrolyte to deposit 1.2 gram of copper. So we have our X now to be equal to 193,000 times 1.2 divided by 64. And that makes X to be equal to 3,618.75 coulomb of electricity. So now that we have gotten the quantity of electricity that was passed through the electrolyte, then we can now go back to the formula Q equal to IT. Q, which is the quantity of electricity, has been calculated to be 3,618.75, then equal to, in the question we are given the quantity of the current to be what? 3 ampere times the time taken, which is what we were asked to calculate in the question. So by the time we make T the set of the formula, we have T equal to 3,618.75 divided by 3. And then we have the final answer T to be equal to 1,206 seconds. And that gives us the time taken to deposit 1.2 gram of copper. And that makes the final answer. And then for this same question, in cases where I am not required to show my step-by-step calculations, probably in computer-based tests where the questions are in form of MCQs, multiple choice questions, where I just need to solve and pick my answer from the options given in the question, then there might not be a need for me to go through this whole long process to get my answer. Even for the first question that was solved, there is actually a much more shorter method that can be used to get the answer for this question. That is simply by using the direct formula. Now, you remember that when I was discussing about the first law of electrolysis, Faraday's first law of electrolysis, we stated that M is equal to KIT. And we also stated that K is equal to capital M, which is the atomic or molecular mass, over Faraday times V, where V is the valency or charge. So by the time we combine these two formulas together, we can have that small m, which is the mass of substance deposited, to be equal to capital M times IT all over F times V. So we can simply make use of this formula to directly get our answer in cases where we are not required to show step-by-step workings. So let's make use of this same formula to solve this question and see if we would get the same answer. So we have M equal to capital M times IT over F times V. Now let's go back to check the parameters that were given in the question. We're given the current I to be 3 ampere. We're given the mass M to be 1.2 gram. So current I to be equal to 3 ampere, and then the mass of copper deposited to be 1.2 gram. And of course our capital M, which is the atomic mass of copper, is equal to 64 gram per mole. Likewise, F, which is a constant, is 96,500 coulomb, and V, which is the valency or charge of copper, is what? Copper is Cu2 plus, so that means the valency will be 2. So using these parameters, we can substitute into the formula and get the value of the T, which is time taken. So we have small m to be 1.2 equal to capital M, which is 64, times the current, which is 3, times T, which is our unknown, divided by F, which is 96,500, times the valency, which is 2. So from here, if we make T the solid of the formula, we have T equal to 96,500 times 2 times 1.2 divided by 64 times 3. So when you solve this, well, you'll end up getting the same answer, which is 1,206 seconds. And we have that as our final answer. So you can see this method looks more precise and shorter compared to